Yeah. Well, you want to come in here?
Is that the coffee?
So, yeah. I'll move down. The Russian's good.
As good as my English.
We're in trouble.
Now you talk about the same thing as me. In trouble.
Sorry? Yeah,
Same thing.
just make sure you put it there.
No, it's another.
I'm sure you will be told. Yes, actually, this is go.
My Russian is not that good. Wait, I can't do it. I'm still. And you find out you have this. You just place the. Can I check my service?
But
We don't right away.
so this is going to be
What you need to
No, I was just doing it.
It's a 25.
Yeah.
I think it's missing here.
I must see you.
Okay. Look, the front, in front, in that.
So I know there's a lot.
Yeah. Let's try to do that. Where's the? It's there. Yeah. Something else we're missing there.
Well, in Pisa, I thought
Again?
in front of the
Good. Again, there's something missing.
Я ничего не слышал, понятно.
No, it's fine. So we just go one further.
Ah, okay. Okay.
Go one more.
Okay.
Куда надо делать? Ну, я помню,
Да, мы еще погуляли хорошо.
That's it. I was
Может там поближе сесть, нет? Да.
Давайте, что вам сейчас? Пойдем?
Отключил.
Right, Dr. Otter, this morning we're going to change gear a little bit. Yesterday we heard about hyperpolarized novel gases and of course more general aspects of biomedical, biophysical interactions. And today we should talk about carbon 13. And the first speaker will be Peter Morris from the Spectroscopy Imaging Center, talking about applications of 13 DNP to disorders of brain.
Thank you, Thomas. Can you hear me without the microphone?
Yes.
First, it's a great pleasure and relief to be here for my travel adventures. And thank you for last night. That was a wonderful trip. Without that magnificent scenery and your great company, I would have fallen asleep after 5 minutes. I really appreciated that. What I'm going to try and do this morning is tell you a little bit of the history of MR in Nottingham for 5 minutes or so, and then show you some of the things that we can do with conventional magnetic resonance spectroscopy, what the challenges are, and why DNP can offer some solutions to those challenges. And then it will be for later speakers to explain in more detail how you can use the DNP. So, we have a long history of MRI in Nottingham. I think this is the first ever meeting. And there's some interesting figures here. This is Paul Outerber. And over the back of his head, this is Sir Peter Mansfield. So these two shared the Nobel Prize for MRI. But in between them is Richard Owens. So down this centre, you have 3 future Nobel laureates at this first meeting. And the message to the young students at the back: if you want your Nobel Prize, you know where to stand. It's in the middle. So I have a question for you. Only Russian PhD students, where was I? I'm in that photo.
Just in front. Are you picturing?
Sorry?
You're taking photo?
No, I'm in that. No? I haven't changed.
That's what you mean.
Okay.
Right on the extreme end. So,
Yeah.
PhD students, don't stand there. There's the place.
Okay.
That's so 70.
Okay. So, and at that time, of course, MRI was in test tubes in conventional NMR magnets, and so you couldn't put very large objects in. Peter Mansfield liked to put vegetables. He used to go into his garden and see what he could find. One of his favourites was this okra seed pod. The other thing he managed to fit in was his research student's finger. So the research student had to give up their fingers for his experiments. It's all right, they remained attached to the fingers. But that was the very first image to show live human anatomy. So that was the first live human MRI scan. And actually, it was that image that persuaded our Medical Research Council to fund the development of the human MRI. Interestingly, our Physics Research Council didn't believe this could work because they thought that, or their reviewers thought that imaging techniques were limited in the resolution by the wavelength of the radiation that was used. Since we were using radio waves, the wavelength of 300 meters, this probably wasn't going to be very good, but of course it doesn't quite work like that. So anyway, Medical Research Council funded that. This is Sir Peter thinking about what a gradient system for a whole body system might look like. And this is the first body scanner. So there's the electronics all home built. This is Ian Pikett. This is me. That is Sir Peter, and yes, he is in the magnet vertically, not horizontally, because that's the way we did the first experiments. We came from a background of solid-state NMR, and you used a separate receive and transmit coil, and you got more sensitivity if you could have a solenoidal coil than if you had an open saddle coil. So we wanted to have a solenoid, but we couldn't therefore put that on the axis of the magnet, because then the B1 and the B0 fields axes would coincide. So the solution was to put the person in vertically. So he had to climb in, and then the gradient coils were bolted in around him, so he could not get out. And that's how that first experiment was done. And that's picture of it in 78. That is Peter's abdomen. This is the press conference afterwards. It didn't generate a tremendous amount of interest initially. So, of course, well, it wasn't just for that, but for the development of in particular, high-speed MRI, EPI, and its variants that Peter shared the Nobel Prize for medicine with Paul Lauterbach in 2003. Well, what's changed since those early days? Magnets have got higher in field. That first magnet was 0.1 Tesla. This is our 7 Tesla system that came from Nottingham in 2005. It's the first one in the UK, the second one the first one to be supplied by Philips anywhere, and the second one in Europe. And that was Sir Peter and I looking at some of the first results. And of course, with the increase in field, we get increase in signal, and we can use that to get greatly improved resolution. So now, very much sub-millimeter isotropic, perhaps down to, we routinely run at 0.4, 0.5 millimeter isotropic resolution, and if you push it, you're getting down into 100 microns or so. So, tremendous improvements. But I'm more concerned about spectroscopy, and there are advantages of high field for MRS too. We get more signal to noise, we can get better spatial resolution, same as for MRI or scan times, but we also get increased spectral resolution, so we can see more species, and there may be some simplification of spin coupling patterns. So let me show you a few slides on MRS. So here's a proton spectrum of the brain, actually my brain. At 1.5T, you can see NAA, creatine, and choline. These are the 3 main peaks that show up in typical hospital scanner. NAA is a neuronal marker, and I was particularly pleased to see that at least when this was recorded, I still had some neurons left in my brain. Maybe if I repeated it, that would have come down a bit, but let's see. As you go up in field from 1.5T, you start to see some of these more interesting metabolites. The amino acid neurotransmitters. And as you go to 7T, you can separate these out. So at 3T, you can't really separate glutamate and glutamine, but at 7T, you can. And that's a feature of the improved spectral resolution. So you can see about 20. So there's that brain scan broken down into 20 different components. So That's interesting because in some diseases there may be changes in those metabolites. The one that we've been looking at most recently is schizophrenia, and we're examining the hypothesis that that has something to do with failure of glutamate metabolism. So we've been looking in key regions of the brain, in new onset schizophrenics and in chronic schizophrenics, comparing them with age-matched controls to see if we can see changes. And indeed there are, but they're quite subtle. There are other possibilities. One can try and do functional MRI. So functional MRI has been very popular and very useful. The functional MRS is a challenge. The changes in activity must be supported by changes in metabolism. You need more energy. You ought to be able to see that in proton spectra. So it was one of our first attempts. We had a flashing stimulus, so this stimulus flashed on and off at 8 Hertz, and it was intended to stimulate the visual cortex at the back of the head as much as possible. And there's reason to expect that there might be changes in the levels of metabolites. So the brain uses glucose pretty much exclusively to provide its energy. So we might expect, as we stimulated and the visual system responded, that the glucose might go down. Maybe we get a transient increase in lactic acid as we have an initial mismatch between anaerobic and oxidative metabolism. And we should have some more neurotransmitter activity. And the neurotransmitter will be glutamate, which is released. So we get more glutamate release. That glutamate is actually taken up, converted to glutamine in surrounding glia, and then recycled. So the neurotransmission is a cycle of glutamate release to glutamine to glutamate. And we reasoned that if we were increasing this, we might get a change in the balance between glutamate and glutamine during the activity. So what did we see? Well, here are some of those metabolites, and there's significant changes you can see in red. So here's glucose. So the blue is rest, the red is during activation, and the following blue is the subsequent period of rest. So you can see during the stimulation there's a decrease in glucose that's significant. There's a slight increase in lactate that's also significant. And in terms of that neurotransmission cycle, indeed you can see an increase in glutamate mirrored by a decrease in glutamine, and these are roughly in balance. So it's the same amount of glutamate plus glutamine, it's just you've got more of one than of the other. That balance changes. But you notice that these changes are really very small, 2%. So that's sort of an interesting academic experiment to do, to explore this. It's probably not a great technique to try and use clinically, because if that's the normal response and you want to look for a changing that response, I guess you're talking about the second derivative. You're talking about a change in a 2% response. So it may be you have a condition where the system doesn't respond at all and it's way off. But if it's more subtle than that, that's going to be a challenge. So that just shows you that we can follow the time courses in more detail. We can see this decrease in glutamate with time of stimulation, the increase of lactate, and so on. And that's largely possible because of 70 brute force IP. How can we take that further? Well, those cycles that I was pointing out, we might get subtle changes in the balance of metabolites, but basically we've got fairly fixed pools, and what happens is you go around the cycle faster. So if you want to generate more energy, you go around the energy producing cycle faster. If you've got more neurotransmitter activity, you go around that cycle faster. But the actual levels of the metabolites may change really very little. So it's rates rather than concentrations that are important. And how do we get at rates? Well, we need to put in a label. So carbon-13 is a great label because carbon, or the majority of carbon, is carbon-12, which is magnetically silent. 1% is carbon-13. But if we replace the carbon-12 with carbon-13, then we can follow that trace. And there's a history of that. Actually, the very first person to recognize the possibilities of carbon-13 was none other than Paul Altabert. So he was well known in the NMR world before he got into MRI. So in '57, he was introducing the world to carbon-13. And it got used to study brain metabolism in the 80s. So we did the first experiments in brain tissue, and then there were first in vivo applications, and it went into man in the 90s. So how does this work? You basically infuse glucose into a vein, which we arterialize. So, you put the glucose into a vein, and you pretty much replace the normal blood glucose with carbon-13 glucose. So it's not a small label, it's a replacement, effectively. So you would have a large bolus injection at the start, followed by a continuous infusion to try and achieve enrichments of up to 90% of carbon-13 labeled glucose in the blood. So that's a lot of glucose, maybe 50 grams of carbon-13 labeled glucose per experiment, so it's thousands of pounds per study. And then we monitor what's happening, in this case, in the brain. So here's an example. Here's a series of spectra at different times, actually running out to 2 hours. And this is what we feed in. 1C13 glucose. You can see that appear really very quickly in the brain. There's the signal. The glucose goes in through glycolysis. We actually don't see pyruvate because it's present in relatively low concentrations. We would see lactate if any were produced. We don't, by and large. That then goes into the TCA cycle, which is the main energy producing cycle of the body. And actually, measuring the rate of this cycle is measuring the energy consumption of that organ. So in my sort of physicist view of activity, a really good measure of that is how much energy you're consuming. So I may not know exactly what's going on, but if I measure the energy consumed and that increases, that's one measure of activity, a very nice one, actually. And not only do you get the rate of that cycle and therefore the rate of energy consumption, but the label goes into glutamate, and as I showed you, that's the neurotransmission cycle between glutamate and glutamine. So if you watch the label go into glutamine, you also measure the rate of excitatory neuroactivity. And you can see with time the resonances corresponding to these different species appear. So the first one is glutamate C4, goes through here. You can see it being converted to glutamine, C4, and so on. And in fact, it's very powerful. This is a cycle, so it doesn't just go around once, it carries on. And if the label doesn't disappear and goes round a second time and then into here, it appears in a different place. And carbon-13 is so sensitive that you can see that too. So on the next turn of the cycle, you start to see peaks appearing in glutamate and glutamine, C2 and C3, so in here. And so you can see how many turns around the cycle, and you can do metabolic fitting to all of that. So here's some examples, actually our first examples. So this is the blood enrichment. That's actually about 60% enriched. And here's the glutamate C4 time course. And you can fit that time course and get the rate of that energy producing cycle. So the rate actually is in here. And there are those rates. At the time I made this slide, these were the only measurements that have been done worldwide. They're all pretty consistent, and they're also pretty consistent with the only other method that's to do this, which is by using PET. You've got to double these numbers in order to compare them with these, and it's pretty good correspondence. So we've got a pretty good measure of resting energy consumption. We're also interested in this neurotransmission cycle, the conversion of glutamate to glutamine. And with Proton, with protons, we were trying to see how a change in this rate might give a change in the balance of glutamate and glutamine, and we saw that was only a couple of %. That might this rate change rather more, because that would be a much better measure. Well, there's the measures of those rates under basal conditions, but at the time we weren't able to measure the change on activation. Here's a period of rest. Here's what happens during activation. So you can see the glutamate C4 being labeled. You then turn on the visual stimulation and you see an increase in that rate. So we can measure the increase in the energy consumed, and it's a lot. So we're not talking 2%, we're talking 50 or more %. So as I was explaining earlier, the response is a change in rate, not necessarily a change in metabolite level. You don't have to go and synthesize new metabolites. Nature doesn't work like that. It uses the same pools and it cycles them faster. And that's what you see by measuring rates. So that's beautiful. You get the increase in energy consumption, and you can quantify that. You can say how much extra energy is being used when you're processing that visual stimulus. And we would like to also be able to say what's going on with the neurotransmitter activity. But that's a challenge because in order to do that, you need to see the label appear in glutamine, and it takes quite a long time for that to be labeled. So there's a delay. It first goes into glutamate, you see that quickly, and then it goes into glutamine, and there's a delay in that response. So basically, at the time we did these experiments, we didn't have the sensitivity to be able to do that. And these were done at 3T, and you can guess what I'm going to say next. But let me, because I want to get to why DMP will be useful, look at this time course. These are minutes, and they're running for an hour and 20 minutes. So we're talking experiments that last more than an hour. These are very difficult to do. They're clearly not clinically feasible. They're entirely of research interest. But it's rates we want. And of course, what would be even better is to measure initial rates. We can't do that with a conventional label because it takes time to be able to see that C13. So we have to fit this curve. But if we could measure that initial rate, we could get all that information in seconds or minutes. And that will be the power of DMP. So just to convince you that physicists have a sort of major role in all of this, if one wants to do this in a selected region, you need to have some sort of localization scheme. And we use ISIS on the protons to try and enhance the sensitivity of the carbon-13. We've then done a polarization transfer from the protons onto the carbon-13 in order to get enough signal to do these experiments. And again, we just finished doing these studies in about 40 schizophrenic subjects, and we're waiting on the analysis of the blood samples to actually find out what's going on. So this is our scan protocol at 7T for that schizophrenia study. 95 minutes. We've not had one single patient refuse to, well, we've not had to abort a single study. So once patients agree to this, they're happy to go through with it, which was a huge surprise to me. It gets quite uncomfortable in that magnet after 3/4 of an hour. And they're some of our first results. But I need to, I have hopefully a few minutes, but yeah, okay. So what's the answer? And that's clinical dynamic nuclear polarization. You're going to hear a lot more about this in the subsequent lectures, but we know that we're going to get a huge increase in sensitivity. Here's from one of my colleagues. 10,000 scans average over 2 days of one particular compound, same concentration, one scan in 5 seconds after DMP enhancement. So huge improvement in sensitivity. And all the studies done so far have been using 1-carbon-13 pyruvate, which is an important link between the anaerobic and the oxidative parts of metabolism. And we can follow that label into lactate and alanine if it doesn't go into this TCA cycle I've been talking about, or if it does, it actually comes off as CO2 and appears in bicarbonate. So these are all one step away from pyruvate, and it allows us to measure the activities of these 3 enzymes. And in particular, this one is really important, as you'll hear later. Very often, if there's mitochondrial deficiency, the clinical answer is to try and stimulate this enzyme, and there are drugs to do that. And the substrate is actually measuring the activity of your drug target. So this is a perfect scenario for clinical application. And here's an example showing that in rat heart. The pyruvate being converted into lactate, alanine, and bicarbonate, and the time courses. And the key thing to look at is we're now not looking at minutes, we're looking at seconds. So, of course, it has to be seconds because the label only lasts that long. But actually, if you were to imagine doing this clinically, then an examination that lasts a minute is just perfect. So, just with a couple of slides to finish up, we're interested in neurodegenerative diseases and the classical ways to look for changes in structure, which you can see in some 7T ones in Alzheimer's disease. Those structural changes come late. What happens early? Well, we can look at these same enzymes from pyruvate, and there's evidence that this is compromised in dementia, in Alzheimer's disease. We would like to look a bit further than those first three metabolites, the lactate, alanine, and CO2. And in order to do that, so do it this way again. If we put the label into the 2 position of pyruvate, and that still has a fairly long T1, then we can see further down into this neurotransmission cycle that I've been talking about. So that's our next target after 1C13 pyruvate, is to just move the label across, and then we can hopefully see further through this pathway. There's evidence of a failure in one of the brain cell types, glial energy failure, and we can probe that if we were to label acetate. So that we don't do at the moment, but if we put a label in acetate, then we can follow that through that cycle, specifically in this one cell type, and probe components that we believe are compromised in these neurodegenerative diseases. So I heard yesterday that the average Russian doesn't live long enough to suffer from neurodegenerative disease, but you will soon, so this will be important. Hopefully I set the stage for the speakers that will follow, and it just remains to thank all my colleagues at SPMIC and thank you for listening. I'm happy to answer.
Right.
I was just wondering, as a future clinician, I think the perspective of those things you mentioned on science and Alzheimer's patients, what do you regard it as a biomarker?
I think it's too early to say. There's 2 things, aren't there? One, I think this is going to be a research tool. We're going to find out whether that's important rather quickly. And if it is, of course, the hope is that it will be a biomarker. And the hope that I hold on to in particular for this technology is yes, it's challenging. At the moment, it's expensive. But the great thing is it's quick. It has to be. And so, if you can find a useful biomarker, it's something that you could deliver and costs will come down. So I'm very hopeful. There is no way that the earlier experiments I showed you with carbon-13 fusion, that you could use that in the clinic. But this I think you could do, and I see that as the bridge between the 2. Thank you.
One historical question. What connections had Roterbor and Peter Mansfield before and after the invention?
Okay, you maybe need to give me a few glasses of vodka to get the full story, but actually quite good. Paul Alpha used to come to Nottingham quite a lot, and we used to have meetings. We had some NATO funding that connected Paul Alpha actually with 2 groups in Nottingham, Peter Mansfield and Raymond Andrews. And so he used to come, and we would have a little conference, and those were each group trying to show the other that they got better results. So it was sort of show off what you've done, but actually that stimulated activity. So and I visited Paul's lab a few times. So actually, there was certainly a feeling of competition between the two groups, but it was a friendly one. And that has not always been true across the story of MRI, and you can get into the office to get a bit more of that. And then after the Nobel Prize, I think probably by that time, Paul had moved from Stony Brook to Urbana and was in not great health, and actually nor was Peter. So I think they probably didn't interact very much. But yes.
Yes, okay, thank you.
Yeah.
Because what I want to add to what your comment is that for the future, I think it will depend, you can see it depend on the intervention that we do, the physiological response. If the physiological response is higher, you might be able to pick it up with DNP and therefore you could clear in that case. But you have to have a big response to it. So you'll be able to detect.
Yeah. Do you want to move on or do this?
Yeah, so just give a quick response.
No, that's fine. No, I was just looking. Did you have a question?
Oh,
Yeah.
sure, sorry.
Sorry. The question is, Alzheimer is a part of dementia.
Yes.
So there is a general form.
Yes.
Does the metabolic metabolism show the change in Alzheimer's disease specifically, or a general form called?
I think these are going to turn out to be a fairly general mechanism because it's a key metabolic control point. And so I don't think it's going to be specific, and that's both an advantage and a disadvantage. But in terms of sort of mechanisms, there are plenty. They've not really been adequate, so the jury's still out on what it is. But we know there are changes there, that we do know. And here's a way of measuring them. In situ, actually at the point where it matters. And that, I think, gives us a lot of hope. I mean, it may tell us that actually that's not relevant, that would be disappointing, but it would still be helpful to the field. Or it is relevant, in which case, we have great biomarker. But either way, there's a big future for the technique.
All right, let's thank our speaker again. From the International Tomography Center in Buenos Aires, Ms. Buller.
No.
He will be giving us theoretical treatment about the advantages of pulse over our EMP.
Hello, dear colleagues. I'll give not clinical usage of DNP. I'll be a little bit more theoretical. I'll speak about the advantages of pulsed Hauser DNP compared to continuous wave DNP. My talk is called theoretical treatment, but also some comparison to the experiments also will be given. You can see the outline of my talk. I'll answer the question why it can be preferable to do pulsed DNP, speak about the theory of pulsed Hauser DNP, and then continue to comparison with the experiment and conclusions. So, you know that the main problem of nuclear magnetic resonance is relatively low sensitivity that is proportional to nuclear polarization that is very low in thermal equilibrium. That's why we use hyperpolarization techniques, and one of the technique is the DNP that is based on transfer of electron polarization to the nuclei. in thermal equilibrium, electron polarization is much bigger than nuclear polarization. So it allows one to get the enhancement proportional to magnetogenic ratios, that is 660 for protons. For other magnetic nuclei, it is even bigger. In liquid state, there is only one DNP mechanism, that is the Overhauser mechanism. I'll say a couple words about how it works. Here you can see the energy level scheme for a system with one electron and one nucleus. Here's the electron Boltzmann, and here's the nuclear Boltzmann. Here the electron T1 and nuclear T1 relaxation rates and cross relaxation rates, double quantum and zero quantum. If we also add the EPR pumping, the fast relaxation path caused by the electron relaxation is blocked, and cross relaxation leads to transfer of polarization from electrons to nuclei. I'll speak about it at a very simple example. Here the circles are the relative populations. In thermal equilibrium, the populations look like this. Here's the electronic Boltzmann. The pumping makes equal populations of these two and these two levels. And cross relaxation, for simplicity, we have only W2 rate. Now works and brings the populations to the electronic Boltzmann. So thus the nuclei achieve the electronic Boltzmann polarization, and that's great. There is a famous formula that is well known for everyone who deals with DNP. Here's the ratio of magnetogenic ratios and three factors, coupling factor that shows how well the cross relaxation works. The leakage factor, that is the ratio of T1 relaxation rate caused by electronic caused by the electrons to total T1, and saturation factor that shows how well the electronic transitions are saturated. DNP, for instance, in nitroxides, when we saturate one of the EPR components, allows one to achieve enhancement of minus 110 for N14 nitroxides, or minus 165 for N15 nitroxides. That is great, but the problem in DNP is that we have to fully saturate the electronic transitions in order to get such big enhancements. And it can cause heating of the sample for several degrees or several dozens of degrees, and that's not very good, especially in clinics. So the idea was to minimize the average pumping power, and this is the motivation paper for our work. Here, Alechi and Lurie investigated whether the pulsed way can be preferable. Actually, from this figure, you can understand whether it is good or not. But what was interesting is this something that looks like some coherent effects, and our motivation was to answer the following questions. What is the physics of pulsed Overhauser DNP? How large can be the enhancement? And what is the role of the coherent effects? So, how the pulsed Overhauser DNP works? Here you can see the applied pulsed sequence. We thought that the period of this periodic pulse sequence should be comparable to electronic T1 for sure, and the whole pulse sequence should be comparable to nucleate one. That's why it will be many pulses here, more than 1 million. And that's why nuclei do hardly affect evolution of electrons. That's why the transfer of polarization from electrons to nuclei can be calculated in the following 3 steps. Electron spin evolution is calculated taking into account parameters of the sample and of the pulse sequence. Then everything is solved for the quasi-stationary approximation, and after that the flux of polarization of to the nuclei is calculated. So the idea looks like this. Electron spin is flipped by a pulse, then it relaxes, then it is flipped once again, and so on. During the whole pulse sequence, electronic spin is far from the thermal equilibrium, and that's why the polarization is given to the nuclei, and DNP effect slightly grows. So the best case is when, on average, the electronic spin is somewhere around 0. What about the quasi-stationary approximation? If we look at the pulse experiment from the very beginning, the electronic Z component of the magnetization is flipped, then it relaxes, and so on. It can be divided to 2 contributions. Contribution 1 is the same for each period. Contribution 2 is not the same, but it rapidly decays because of huge number of periods. Only contribution 1 is important to calculate the DNP effect. And what is important, this can be done not only for that very simple pulse sequence, but for an arbitrary pulse sequence. The flux of polarization is given by the difference of electronic magnetization and thermal equilibrium. And the formula in the general way looks similar to the formula in CW case, with the saturation factor replaced by the average deviation factor. So let's go to the modulation. Let's look what will happen if we have EPR spectrum with 2 components, and we do pump at one of them. You can see that even for such low percentage of time of pumping as 10%, for proper parameters of the pulse sequence, the enhancement is close to theoretical maximum of -165. That means that we apply 10 times less pumping power and do not lose much in the enhancement. That's great. Of course, the lower is B1, the longer time you need to apply this optimal pulse, that is the pi pulse. And due to T2 relaxation time, this enhancement achieved gets lower. There is one more very interesting thing. If we have 2 components and this delta that is bigger than B1, we still can achieve, we still can get the enhancement from the off-resonant component for short pulses that are shorter than 10 nanoseconds. You can see from this picture. With real pulses, this is really demanding, but as I'll show later, still this effect works. Here you can see the comparison for a homogeneously broadened EPR line. The enhancement for proper parameters of the pulse sequence is always bigger for the same average pumping power. So let's proceed to the experiment. The pumping was done at one field, then the sample was mechanically moved to the field where the NMR detection was done. So here you can see that the theoretical modulation fits very well to the experimental data. Beatings are more pronounced at the upper figure due to bigger V1 amplitude. From damping, the relaxation times T1 and T2 can be obtained. And as you can see, nearly full theoretical maximum of the enhancement was obtained for a duty cycle of 10%. Here is one more interesting thing. Here's the N14 nitric oxide, and it has 3 components. The theoretical maximum in this case for one component is -110, but you can see that the enhancement sometimes is bigger. That is due to that contribution from the off-horizon components. So we can say that the general expression for the enhancement has been obtained, and saturation factor in that expression corresponds to the and the average deviation factor in that expression corresponds to the saturation factor in CW case. An arbitrary pulse sequence can be treated. Coherent spin motion is really important in such experiments, and what is most important is that pulsed mode of pumping seems to be advantageous for multi-line EPR spectra and for broad EPR spectrum. So I would like to thank my co-authors, Russian Foundation for Basic Research, and you for your kind attention.
I have a question. So I'm sure you mentioned it and probably I missed it. So when you actually, how long does it take you to take your sample from the EPR stage to the detection stage? So because it shows that there is some mechanical aspect to it.
Yeah, here's the experimental setup. It takes less than 0.3 seconds, so it is faster than nuclear T1.
So you are moving it in the gradient, right? Do you
yes.
observe any depolarizing effects during the gradient?
Sure.
And how big they are? Okay.
Not so big.
Okay.
So the polarization remains and the enhancement is observed.
Okay, so assume, so one of the advantages that you can go to overall lower power, if I understand that, is that a given polarization level that you can reach. And so the excitation width of the pulse is fundamental here, I guess, to some extent, and of course the fact that you can invert. This is the excitation width you calculate, of course, based on some broad homogeneous borderline. Is that always the case?
The excitation width actually depends on the shape of the pulse. That's why we can, for short pulses, excite far of the EPR components that are far from the resonance.
Now, I recently heard about a frequency sweep kind of EPR that must be for similar reason advantageous, when you just sweep the Of course, you don't invert there, you just cover a larger area.
Yeah, I thought about that, but I can't say anything exact yet.
Could be the appendix streams that you can use. Anyway, but that's very interesting work. Let's move on. Let's all thank our speaker again. Our next speaker is Martin, also from the International Tomography Center in Novosibirsk, and she will talk about the topic that's using optical methods to hyperpolarize a technique called KidNet.
I'll speak about exchange interaction and photo-induced intermolecular charge separation, CDNP measurements of TX8 IRs. In my presentation, I will talk about CDNP. It is a chemically induced dynamic nuclear polarization and how it is applied to the analysis of magnetic interactions. In this method, we produce transient radicals by light and observe an amount of polarized. Sorry? Yeah. In my presentation, I will talk about CDNP. It is a chemically induced dynamic nuclear polarization and how it is applied to the analysis of magnetic interactions. In this method, we produced transient radicals by light and observe an amount of polarized product molecules that is selectively formed in the recombination reaction of short-lived radicals. Here is some basic principles of CDNP phenomena presented. CDNP results from nuclear spin selective singlet triplet intersystem crossing in radical pairs or biradicals. It relies on principle on spin conservation. All chemical reactions are spin selective, and they are allowed only if total spin of reactants is identical with spin of products. Magnetic interactions, only magnetic interactions can change spin. And nuclear spins involved in the recombination reactions, and on the nuclear spins can by their magnetic moments and hyperfine interactions, they involved in intersystem crossings. And their magnetic reaction products are enriched in certain nuclear spin configurations, and we observe an NMR with abnormal intensities, emissive or enhanced absorbance spectrum. As I already said, CDNP is formed in the reaction of recombination of short-lived radicals. In most cases, such radical pairs are generated by UV light. For example, we generated radical pair in singlet state. Then this radical pair can recombine, or it can go to triplet state and the radicals go apart. Here is a simplified vector representation of electron spins in radical pair. Two spins, one half, can form singlet state, or two spins, one half, can form singlet states or triplet states. At high magnetic field, only S and T0 levels can be considered. To recombine, radical pair should go to singlet state. To get nuclear polarization, we have to introduce at least one nucleus with spin one half in our radical pair. At in the certain distances between the radicals, and by the action of hyperfine interactions and difference in the G factors of two radicals, electron spin states can change. The rate of this transition from singlet to triplet state are not the same for different nuclear spin states. Let us assume that for the nuclear projection alpha, this transition is faster than for nuclear projection beta. In this case, our Gemini products will be enriched with nuclear projection alpha, and nuclear projection betas will go in volume. And in our Gemini spectrum, we will see enhanced absorption in NMR spectrum. In bioradicals, radical centers are linked by a carbon change, and in bioradicals, radicals cannot be separated and go apart. In this case, electron-electron coupling or exchange interaction J is important. At small distances, when J is large enough, exchange interaction blocks interconversion, while at the longest distances, J becomes smaller and the intersystem crossings proceeds. At magnetic field of B0 is equal to J, level crossings is a level crossings. There is a level crossings, and in this. And here, hyperfine couplings induces transitions between singlet and triplet states, and the total spin of one nucleus and two electron spins is conserved, and recombination occurs. Here, the structure of investigated diide molecules is shown. These compounds were synthesized in Würzburg by Professor Christoph Lambert. The scheme of photochemical processes in this diode is as follows: after the light quantum absorption, charge separation is occur, and then this diode occur in the charge separated state for several microseconds, and then after the spin selective charge recombination, CADNP is formed. We can study our molecules by two possible ways. The first way is a time-resolved CADNP at high magnetic field, and the second is magnetic field dependence. For example, by CADNP by time-resolved CADNP, we can obtain the following information about our structures. It's about our radicals. It's isotropic hyperfine interactions. Also, it's rate and mechanism of radical reactions, nuclear biomagnetic relaxation times, and also we can study polarization transfer. And by magnetic field dependence, we can obtain G factors of radicals, hyperfine interactions, exchange interaction, and also study polarization transfer. From Gemini CADNP spectra of high magnetic field, and isotropic hyperfine couplings we obtain. Also, we can study field dependencies of CADNP formation by variation of external magnetic field. The experimental protocol is as following. The first step, it is a polarization at low magnetic field by light irradiation of our sample. Then the fast transition of our polarized sample at high magnetic field, and then the detection of NMR spectrum of our polarized molecules at high magnetic field. In this way, proton CADNP spectra at low magnetic field was obtained, and we see that signal-to-noise ratio of relatively diluted sample for NMR spectroscopy was obtained. Was obtained by only one scan, NMR scan. So by varying external magnetic field, proton field dependencies for each polarized protons in our diode could be obtained. Also, we can measure CADNP carbon-14 spectra with natural abundance of carbon-14 in our diodes. You can see that if in case of usual NMR spectroscopy, we will need to accumulate more than 1,500 scans to get appropriate signal-to-noise ratio. While in the case of the CADNP, CADNP spectrum we obtained only by 32 scans, and it took about 20 minutes, and the concentration was about 100 micromolar. Also, we obtained CADNP field dependencies and natural C13 abundance, and C13 CADNP enhancement was bigger than 3,000 in this case, and also sign and value of exchange interaction was determined. And to sum up, chemically induced dynamic polarization, CADNP, it is a hyperpolarization technique that can give us information about magnetic interaction in short-lived radicals with atomic resolution. And high enhancement factors can get this study very sensitive, and only few micromolar concentration of geminate products of radical radiation are detectable with high spectral resolutions. CADNP serves as a fingerprint of short-lived radicals, and for hyperfine coupling quantums for geminate spectra and G factors from magnetic field dependence could be obtained, and for bioradicals, information about exchange interaction is obtained. And now I would like to thank my colleagues from International Tomography Center and also from Germany who synthesized our compounds. Thank you for your attention.
Your enhancement factors, what kind of enhancement factors do you typically get? And what kind of enhancement factors do you typically get?
It's a comparison from low field when we obtained our C13 spectrum to the usual NMR spectrum.
And how much the values?
Here is about 3,000.
I know that's not so important in the case of what you're doing, but can you give a rough estimate what the hyperpolarization level is? What's the spin polarization in this case? What field strength is this?
The field strength was 20 millitesla here, and we compare to 9 Tesla, 400 megahertz.
Any other questions? Well, let's take our small speakers. No, let's take our speaker again. We have and it was supposed to go to 55. Yeah, it's supposed to. So if you come back here at 5 before the hour, 5 minutes before the hour.
Не, я ему передал ваш телефон, он должен сейчас в ближайшие 15 минут где-то заявить, он просто не был на телефоне. Вам спасибо. Хорошо, договорились. Спасибо. Часа до 4.
Так, ну что?
Так, это переведите на название.
Ну, сейчас я переведу. Мне нужно...
Нет, я с вашего должен зайти в ваш личный кабинет. Я платил.
Я тогда.
Да, у вас есть?
Да.
Дадите тогда в этот Сбербанк. Сейчас мы отметим, сколько человек. Вот сейчас. Arno is going to be on.
So that's all taken care of?
Oh, we took care yesterday on the boat.
It's very strange.
Okay. Чего ты боишься? А, да. You guys, are you allowed to have excursion?
In an hour, we are going to have an excursion to the main building. Are you going there? Молодец, что пришел, внизу кофе брейк.
Большую камеру, по-моему.
Большую?
Она не нужна пока?
Большая какая, в смысле? А на нее можно сделать как в камеру?
Yes.
Я перед отправил, но
Ну, я не знаю, если эксперт.
открыть, да?
Работается.
Он, да.
В общем, как вчера это, если что, тогда звоните,
Ага.
я подбегу.
Спасибо вам. Там нет. На первом этаже, вот прямо около лестницы. Где он даст, расскажу. Нашли, да? А, сделать. Выбирайте там платежи, дальше будете МДУ, и выбирайте музей телевидения. Вот смотрите. Попробуйте. И просто сумму. Ahmet çok kötü опять, если поставить, конечно, показывает. В смысле, он скажет, что он бросать. А, ну да, да. Нет, я хотел, чтобы он делал. Чтобы он. Ну, посмотрим, может мы развернемся. Если вы развернетесь,
I'm going to come and sit here.
Yeah, please do so. Arnaud, comment? Is it live?
Yes.
I am talking first, tell him.
Okay.
Tell him.
You have to write it.
Okay. First. Oh my God, can I just,
And it's always like.
because I'm, no, we are.
Well, you know, it's better. He's just calling us on video, so you can just.
Okay, after. Okay, can I go first?
Yes, of course.
So can I just, he responds, shall I come here?
You don't get much clue. I suspect it keeps similar.
I'm not sure, I think it is.
Yeah, no, it's.
Yes.
Good morning.
Oh, good morning. Salut Sébastien.
Does everyone see you? Okay, great. Everyone is here.
Okay, that's good. Let me figure out how I can show my slides. So, options.
There is a plus sign just when you move your.
Here we go. I got it.
In the bottom.
I got it. So now if I do just, where is my time? Hold on 1 second.
Yeah.
Okay,
Yeah, now it's working.
here we go.
We don't want to see you.
Is that okay?
Well, more or less, it's okay.
So now, yeah.
You can see the English from the computer. Yeah.
I want to try it on a different laptop.
Okay.
Okay, now it's okay for you.
Yeah.
Okay. We shall just you will have a talk of Sebastian, and after that we shall contact you. So you can be online. So not to close this conference.
Sure, no problem. I'll wait. No worries.
Okay, you just wait 20 minutes.
Yeah, no worries.
A bit more, it says.
Yeah, that's fine.
Okay.
No worries. Okay.
Great. See you
Right, let's get started. Our next speaker is Sebastian Sears from the University of Nottingham, and he will tell us all we need to know about the metabolic imaging and humans using hyperpolarized current.
Thank you very much, Thomas. So, I am not a clinician. I am not an NMR physicist. I am a biochemist, and I'm going to give you my kind of point of view of metabolic imaging in human using hyperpolarized cephalic magnetic resonance. And what do you need to know if you want to, in the future, use this technique in this country? And also show you what you could get from this technique, and in particular to understand how to, as a tool or biomarker in precision medicine. So I will exclusively talk about metabolic imaging in skeletal muscle, in this case in my talk. but it can be this metabolic imaging approach can be applied to other organs. So metabolic imaging in precision medicine involve MRI, as you know, in the muscle, and we can use MRI to get anatomical changes. Also, as Peter described it for the brain, we can measure metabolite content, such as a lipid in the muscle, or the synthesis or resynthesis of glycogen, which is an important metabolite in the skeletal muscle. And this can be done by proton magnetic resonance spectroscopy or carbon-13 with natural abundance in the case of glycogen. The issue here, if you want to use this imaging technique or spectroscopic technique, is that if you give a treatment to someone, to your patient, and in order to find whether this treatment have a benefit, the turnover to find that is sometimes on order of weeks. The time scale takes a long time. Alternatively, there is nuclear medicine techniques such as PET that involve, for example, FDG glucose PET that measure metabolic changes, or also some functional MRI. This technique works very well for cancer, to detect cancer, or functional MRI to detect any kind of metabolic changes in the brain of patients. However, this is not appropriate for the skeletal muscle. The advantage of this technique, because they look at dynamic changes, very quick dynamic changes using metabolic marker, is that the time scale, that you will be able to detect any change in your treatment on your patient is shorter. So basically, we can get an answer in 24 hours or just a week. So alternatively, for the skeletal muscle, what you could do, you could use stable isotope, as described by Peter, is where basically you will have a sugar, for example, glucose, that can be labeled with a C13. And this stable isotope, unlike radioactive isotope, is stable and safe to use in patient one day and the next day and so on. And the problem is that because natural abundance of C13 and biological abundance is low, we need to infuse this molecule to see them, or hyperpolarize this C13, and you can detect it easier. So magnetic resonance spectroscopy in combination with stable isotope has been very successful to detect metabolic changes in cell, isolate organs, animal and human, as described by Peter. And typically, what you will see is that you will have you will inject this stable isotope to someone, and you can look at the fate of this C13, the labeling of this C13 into other species or other amino acids in any kind of organs. And using a sophisticated modeling approach, you can determine metabolic rates. I'm going to be quick on this because Peter has already described this. Or you basically measure metabolism using C13 MRS. What you have to know here, which is very important, is that this approach is powerful somehow in research, but it doesn't give you a direct measurement of metabolic enzyme activity in vivo. And also require high-field MR scanner. So in the skeletal muscle, if you want to use this stable isotope approach in combination with MRS, you will face two other issues, such as presence of fat as well in the tissue and the lot. And although you can suppress it, the labeling of your amino acid will be difficult to see because due to the presence of this fat. As well, as Peter described, is an expensive experiment. Okay, and it gives you, although you infuse that for a long time, the SNR is still quite low. And you can only detect molecules or metabolites that are highly concentrated in your tissue, an order of millimolar. So you are limited in what you can see. And as this described by Peter, the acquisition time is quite long, up to 2 hours. And it's not very appropriate, let's say, in the clinical setup for precision medicine. And finally, what is the most important, what the clinician wants, does, for example, a drug has an effect on this enzyme, and want to know, have a direct assessment of this. And this technique doesn't give you, because it does not give you a direct measurement. Thankfully, with the advance in, let's say, practical advance in dynamic nuclear polarization, we may have a solution to detect, be able to detect the activity of specific enzyme, and therefore use this as a biomarker to determine whether a treatment is working. As you all know, I'm not going to give you a physics talk, is that this dynamic nuclear polarization principle has been already established by Oberhauser back in 1950s, about and can be summarized by this graph, where you have represented the polarization as a function of temperature. Is that if we know that the polarization of nucleus such as C13 is quite low at room temperature, while the one of electron is higher. But when you freeze this at very low temperature, 1 Kelvin, you can achieve for electron up to 100% polarization. And the beauty of dynamic nuclear polarization and the principle established by these people is that if you place your C13 stabilizer top in a MR, in a small magnet, with a free radical with a lot of electron that can be polarized, and cool this at 1 Kelvin, and apply a microwave irradiation, you can transfer the polarization from the electron to the nucleus, and then you will have a C13 labeled substrate with a high level of polarization, and therefore produce high level of signal on your MR scan. What you have to do is to try to have a kind of trick in order to melt this ice cube basically rapidly and be able to inject this solution to someone rapidly. And this was has been established and done by Arden Larsen back in 2003. And the principle has been basically is at the basis of this both preclinical and clinical as a hyperpolarizer machine, where you will place your C13 stabilizer top with a aromatic agent in the center of a small magnet, which adds 1 Kelvin here, and basically kind of is in an helium environment. In there, you apply a microwave where you can transfer polarization and wait up to 2 or 3 hours to reach a plateau maximum polarization you can get for your C13 molecule. And the beauty here is that you will have a system where you can inject hot base or water, and you can dissolve this rapidly and extract this rapidly and be able to inject that to an animal cell or people. And that's what the original paper in PNS did. And they show that you can increase the signal to noise in C13 up to 10,000 times, which was incredible at that time. The problem here is that at room temperature, the polarization decays rapidly. And this is depending on the value called T1. And depending on the molecule, the T1, it can be short or long. And typically it's 60 seconds for 1 C13 pyruvic acid. So what you have to do is to make sure that the MR scanner is quite close to your hyperpolarizer. So in the clinical setting, you have to be quite close. And you have to make sure that you get the molecule to inject rapidly from the hyperpolarizer. So what we do use with the SpinLab, the clinical hyperpolarizer, it's pyruvic acid enriched with C13 and labeled in the carboxylic acid because the T1 is longer, 60 seconds. And you use a paramagnetic agent. And this setup is good because it forms a nice crystal and polarize very well. So I'm not going to talk about that. I'm not going to go in more detail, but what we use is a plastic tube in order to dissolve it that can resist to high thermic shock, because as you can imagine, we can start from 1 Kelvin to 100 degrees Celsius is a lot of shock here, thermic shock. So what we do, at one hand, we have the pyruvic acid, about 1 gram, 1.5 gram, that we mix with this paramagnetic agent. So the solution looks green. It's not very pretty. And on the other hand, you have the dissolution strength containing the strong base, because it's an acid, so we need to make sure that you have something physiologically relevant when you inject. Page 7. And that base will be heated at 100 degrees. And on the other hand, you have the syringe that you get the injectable solution that we use to inject your patient with. And you need, of course, to run, not to run, but to be quick to inject. So what you need to know is that when you inject this 1C14 pyruvate that become now pyruvate, not an acid anymore, because it's pH 7, it will be transported into the cell by the transporter of this pyruvate and metabolized into a pyruvate alanine lactate and bicarbonate, as you can see, through the TCA cycle, so through the pyruvate dehydrogenase complex. Peter has already explained all of this. I'm not going to go into detail, but what is interesting that in the past, people have used, for example, the conversion of pyruvate to lactate as a biomarker for response to treatment in cancer. And this was a very good biomarker. So where you could see that, of course, in the tumor, you have an increase of lactate. And this can be an imaging map of this. And this does not correlate with the presence of pyruvate. This means that the tumor takes the pyruvate and convert it into lactate. Oops, what's happening here? What should I say? So can you stop to watch? Therefore was good. Yeah. So this is one aspect. So this technique has been used a lot in cancer, of course, to detect the Warburg effect and the response to treatment, any kind of treatment in cancer. As well has been used in cardiology to look at heart metabolism, and as well to look at competition between fat and glucose as energy substrate in the heart, and what does diabetes and insulin resistance does to this change in metabolism in the heart. And this has been done by people in Oxford. And you can see that if you fast a rat overnight, you can detect change in the level of pyruvate dehydrogenase complex. So what you can do with these other things that you can do with pyruvate, hyperpolarized C13 pyruvate, is that you can go with a more complex analysis where you can just do modeling and extract parameters such as KPL, the conversion of pyruvate to lactate, the constant, that you can map here in any kind of organ, give you an idea about how much of pyruvate is converted into lactate. In the US and Canada, they are leading the field, and they have already applied this technique in humans to detect metabolic changes in the heart in Canada, and of course in the US, in particular in San Francisco, where they use it to detect metabolic changes in the liver, in the brain, and mostly in people with cancer. But what, in our case, my case, what we want to look at, and what Peter described, is that the activity of pyruvate dehydrogenase complex, because it is a good marker to target in response to treatment in different type of disease. What is important to know in muscle is that, of course, ability to work, we need energy, okay, to feed the muscle and to do this movement. In normal cases, okay, you will have, if you want to run fast or to do a kind of intense exercise, this energy is mainly supplied by non-oxidative metabolism through the glycolysis, and result by an accumulation of byproduct of this glycolysis, such as lactate. And this is because the pyruvate dehydrogenase complex has kind of, we said, a metabolic inertia. It's a bit slow to respond to something. And this is fine for healthy people. So you can do an exercise, you can stop because you cannot do more, and you can feel your legs burning because of presence of lactate. Okay. However, in people who have disease, or for example, people, a group of people, family, okay, vascular disease, we will have an accumulation of this byproduct. And there is drugs at the moment that can target this, such as DCA. And this drug cannot be applied in the clinic because you need to control the activity precisely. People can control and measure metabolic changes using biopsy, but what we want to do is to avoid this in this population, peripheral vascular disease people, where we can use this technology as direct marker of this metabolic enzyme and see whether the treatment has worked in this population. So in Nottingham, we have started in November 2015, and we have all the legal documents since 2017-18, and recently established collaboration with a good medical practice facility in London in order to get this pharmacy kit that contain all of this pyruvic acid. And we have also developed the spectroscopy and imaging method to detect it. So at the moment, we need to finalize some document and be ready to. So we need to do an exercise task to have an intervention to detect change in pyruvate metabolism in the muscle. And we need to recreate this daily stress situation using basically an ergospec that is MR compatible. So where people will be pushed against the pedal while lying in the MR scanner. We also need to use a very small code where you localize the metabolic change in one particular muscle, and as well get only one population of people where only male with similar age and BMI. And this is very important for us because it will reduce variability to detect this, and as well increase sensitivity to physiological response. So what we will do in parallel, we will use phosphorus spectroscopy, well-established technique, that gives us indirect measurement as a control for our experiment. And this is already set up at the St. Petersburg Field Imaging Center. In our case, we will measure these peaks after injection of pyruvate in Proton. And this peak will be converted into lactate, bicarbonate, and CO2. And will give us an information about activity of lactate dehydrogenase, pyruvate dehydrogenase complex, what we want to know, and as well pH changes. And this is interesting because it's a direct marker, it's a very good biomarker of any kind of response to treatment that target this particular metabolism. As well, we will have high sensitivity, which is good as well, so a better, reliable measurement. So how it looks like when you do this experiment. So you will get this pharmacy kit you put in the hyperpolarizer, and you polarize for 2 hours. When you reach a plateau polarization, you press the button to dissolve the solution, and it will pass through a different several tests for concentration of your pyruvate, pH, concentration of your parametric agent, temperature, and polarization. We reach about normally 35%. And we need to match with our criteria of release that we need to show that to the medical team that's going to inject that to the person in the scanner. We also need a power injector because you need to inject it that rapidly. And the prescription that we normally use, what we will use, is 0.33 milliliter per kilogram of this highly concentrated pyruvate over 30 seconds. And as I said, the distance is quite close, so everything will be done in the 10 meter, basically in a room. So this has to be done very rapidly, and has to be done in less than 5 minutes, of course, because you will lose your signal after 5 minutes, completely. So to summarize, this is a long road, and to write what I'll show you take a lot of effort and time, in particular in order to get a level of governance and training. when you have to go through a lot of authorization and write a lot of documents, more than 35 documents. And it took about 3 years to obtain them from 3 different organizations. And we have finally now, or almost, a contract in place with the GMP facility to get this sterile separating pyruvic acid, which took time as well, because we don't have a pharmacy facility to produce that ourselves, so we have to rely on another university. A medical team with at least 2 people trained with life health support, and a qualified person pharmacy that is the guy who can release the drug, I mean the agent in this case. And equipment in your scanner to make sure that you measure all the physiology in your volunteer or the patient inside the scanner. And you also have to tell you, one is that it's a lot of training, and you have to be able to understand how the system works using a lot of research field path. It's different system, but we allow you to learn how to use the system. And as well, as what you have to know, it's not a push button approach, so you need to be well trained. So finally, what we would like to do here in the future, if this proof of concept has been successful in volunteers, healthy volunteers, we would like to apply this in a patient with peripheral vascular disease to know whether our treatment can be detected and whether this technique that can measure pyruvate metabolism is a good biomarker for this treatment. And this can be applied to other organs as described by Pigeon. And as a response to different intervention, exercise, nutrition, which is what we are good at in Nottingham, and in collaboration with 2 centers, the BRC and the Beacon, in precision medicine in Nottingham. And also, we hope, through collaboration with you guys, with workshop or perhaps student workshop, a postdoc exchange. Thank you very much.
Questions? You mentioned that you have to have a qualified person that you release.
Pharmacist, yes, pharmacist.
He or she has not taken quality control.
The quality control is the screen that I show you. So in the spin lab, you will have a part of the spin lab that have a quality control analyzer, where you want a bit of your pyruvate that you want to inject will be taken to and be measured through a cuvette by just optical measurement for concentration. pH. So this is the quality control that we have. So yes, concentration
level also needs to be.
Yes. So as you can see, our certificate of release, we need to be in a range for the pyruvate concentration, and this pharmacist has to tick. Oh yes, we are within range, so it's fine. Let's have a look at the pH. We measure the pH with the spin lab, but as well on the bench we measure with the pH paper. We also measure the concentration of pH, which is a parabenzylic agent. We don't want to have any more than 3 micromolar. Okay. We also need to know the volume as well, of course it's not very important, and the polarization, because we don't want to inject something that has 2-5% polarization. It's not worth it. And I have a long discussion with the medic, and he said that we need to have like something that is sensible. I don't want to take the risk for nothing. So,
the hypersense system has a built.
no, it's a spin up.
Sorry,
hypersense is the preclinical.
Yeah, the spin lab
So yeah,
has a built-in.
okay, and I show you how it looks. You can see here, it's with the computer. It's like a small part. So it's built into it. Yeah.
And other than that, you also need, as you mentioned, from the company, from your collaborators.
Yeah, GMP pharmacy. Yeah.
The original.
Yeah. So we need. You remember, we need. I show you this plastic tube. So we need to have this plastic tube filled in a pharmacy. Sorry. I know. I figured this. This plastic tube need to be assembled in a clean room. Correct. It is sealed through a light laser. Okay. It doesn't look like that, but very much like that. It is sealed. So it's sealed here, and it's sealed another place. And basically, this has to be done in a clean room, and we don't have this capacity. So that's why we need to rely on this.
So you can automate it.
So you will be go into like plastic shield where you open it, and everything inside is sterile. So we have the plastic.
So it's basically like a syringe that you get.
Yes, basically, and the syringe will be released through a filter. And this syringe, of course, has to be not be open, but only put on the injector and inject it. Okay. Galina?
Is there any opportunity for using this technique for long study?
Why not? If you want to detect cancer, yes. No, yes, I think Arnaud will tell us more about it. But I think nobody has done. So what, of course, people have done is that they go through a population of patient, a large population of patients, such as people with prostate cancer, of course, or breast cancer in women, and prostate cancer in men, because it's a large population, you can recruit a lot of people. People with brain tumor as well, and people with diabetes, and of course, you know. So it's easy to, I mean, easy. You have a large population, it's quite easy to recruit. But I guess you could. I don't know. I think Arnaud will tell us more about it.
Well, I was just wondering, how would you deliver
it?
How would you deliver? Because I think the question is how would you deliver it for lung imaging? I guess.
I mean, if you I don't know, if you inject in the blood, it will go to the tumor in the lungs, through the blood.
It has to go through the blood.
Yeah, it has to go through the blood, of course. Yeah. But there will be blood supply to your tumor in the lungs.
Yeah, but it will go somewhere.
As well, yeah, I agree. You go everywhere in the body, but if you just look at your image in the lungs, yes, why not?
Are there any? So, what kind of cancer produce this more?
So people who work in the field just correlate with, people say that with more aggressive cancer, you will have more lactate produced, and therefore, see what I mean? You can Warburg effect, so more lactate, and therefore you can be able to pick up this using pyruvate conversion to lactate as an indicator of aggressivity of tumor. But as well, see whether your drug has an effect on the tumor, and the one good example is to see whether the tumor release or produce less lactate. If you produce less lactate, you can see. This means that your drugs has worked. And because the turnover, metabolic dynamic change, is quite quick, to give you an information like 24 hours, like it's very quick. It's what Kevin Wheeler did in mice, and he could see that after only 24 hours treatment with typical drugs, you could see a reduction in lactate production in this tumor. And he thought, and he hypothesized that this could be a good biomarker to detect any effect of any drugs, okay, in this particular cancer.
Any further questions? That's not the case, please. Let's take on the speaker again.
Thank you very much.
And our next speaker is not in the room, so it might be make it happen.
Okay, can you hear me?
Yes, great.
Okay, excellent. Should I go ahead?
Give me a second.
Okay.
Our next speaker is Arnaud from listed here, XGE Healthcare, so it was in Cambridge. And he will talk about GE spin lab, the production of hyperpolarized molecules for human administration.
Okay, excellent. Thank you for letting me speak here, and I apologize for not being able to make it to Moscow. I would have loved to see you in live, but that's the way it is. So I will present mostly the current technology that's available for human application of dissolution DNP. And as Thomas said, I'm working for GE Healthcare, and I also work on the development of the future technology. But I will mostly stick to what we have today to kind of make you give you an overview of what's needed and where we are and the challenges and what can be done today. So I'm not going to, hold on, let me see if I can go to the next slide. Here we go. So I'm not going to talk about the details of metabolism because Peter Morris and Sebastian Serres already extensively talked about. I'm going to focus on the technology and the physical concepts needed. So you may have seen this type of graph before. As so, if we try to perform MRI on C13 nuclei and even on any nuclei, as a matter of fact, we always trying to increase the polarization of the nuclear spins, because the problem of NMR is that we basically probe only 1 out of 1 million nuclear spins. So it is fairly insensitive in that sense. One way to increase the polarization, as you can see on this graph here, beyond increasing the magnetic field, which is going to give you perhaps a factor 2 or 3, is to lower the temperature. But obviously, this is not something that's feasible in vivo. When you look at the range of temperatures that you have to reach to actually increase the C13 dramatically. So we're talking about sub-Kelvin technology, and even to sorry.
Yes, can you please share your screen?
Oh. No, that's not good. That's not good. I thought you were. That is interesting. Why do you see me only? Because I'm sharing my screen. Hold on. Because Skype tells me that I'm sharing my screen. So I think it's something that on your side you have to switch to the slides. Because
Switch to slides. А где наш командир?
А он сам знает, он знает.
Он все шерит.
Не.
Давай я объясню.
yes.
You have.
So I'm sharing my screen, and I'm my slides are full screen right now on my screen, and it shows the. Oh, here we go. Now it's not anymore. So let me. I start again. Okay. Now it should work, I suppose, right? Do you have it?
No. Can we contact once again? I'll call you.
Sure.
Back.
Sure. That's fine.
Завершите разговор и заново начните.
Okay, I see you. Now I share my screen. And I put my slides up.
No, we don't see you. No, it's okay.
If you don't see me, that's okay.
No, we see you. We
Oh.
don't see this slide.
Oh, that is a bit strange. Did I send you my slides?
Oh, okay.
That's something we can do. Because, yeah, I mean, from my side, it shows that I'm sharing my screen.
Okay,
So,
you know, the thing is, maybe we can just move the. No, we can move his presentation to the in the afternoon. Okay.
So you still don't see my screen, huh?
Yeah.
This is very strange. Because the only thing it says is stop sharing. So I'm totally sharing the screen.
Just try once again. We will.
Maybe Arno also should restart.
Stop sharing. Share screen.
From his side that he has to share his screen.
No, I'm sharing my screen for sure. Yeah, I do that. Share screen. I share the screen. It shows even with the red frame around my screen computers. It shows that you should be able to see it. All right. So what I can do. Okay, Alexander, you have two email addresses. You have the Gmail and the other one. Should I send you the slide? Okay, so I send you my slides right now, and we'll do that.
You know, you can do it through Google Hangouts as well.
Посоветуйте ему позвонить без видео, а потом уже расшарить экран. Так не работает?
Да что ты не ничего не болит особо.
На этом слайде, на том слайде. Почесывается. Сам ставлю сюда добиваться. Ставлю там. Честно. Пакет лет, реализацию просто памяти. Они ее тоже меряют. Они меряют игру. То есть они как бы пакет берут, сливают водой,
Maybe why don't I try calling you? Do you want to do that?
I don't get your email.
You don't even get my email. This is weird. All right, you know what? If you don't get my email, that may be because it's. I'll send you from. I'll send it to you from my Gmail.
You can send it through the Skype via Proton.
Yeah, no, I'll send it to you from Gmail as well. Gmail to Gmail should work because I send it from my G account. Okay.
Это основной вопрос, который возникнет в наших родственниках, да, который хочет
Yeah, I can try calling you just in case the.
Shall we try to make normal I'll call you on the can you call me?
Yeah.
Это отдельно, да. Кто будет заниматься специализацией? Захотели вот завтра море денег, очень хотим. Кто будет заниматься специализацией?
Вот я сейчас существует два Юрий Иванович, поскольку вы хотите, чтобы вы просто сертифицируете вот, и поскольку фармацевтический препарат, там сразу все регуляции. Давайте, по безопасности.
And now I'm going to share my screen. Do you see it?
Everything goes step by step in the wrong way.
Can you see my screen?
Yeah. No, we don't see your screen, so but
You should see yourself. And okay, so I don't know why this is very strange. Okay, so I oh, okay, right. So if you have my slides, then
Yeah, just wait.
okay.
У нас мы-
No, just
Ну,
next.
дело в том, что, знаете, еще такая вещь. Вот у нас вот эта поляризация, да, ну, свойства, да, вот как ну, профессор машина. Можно это сделать с полетом, занимать время, да, и разобраться. Если вы производите чистый зал, чтобы
We shall schedule, we shall, okay.
Okay, so
So we are going to,
I say next slide simply at the end of when I'm done.
Yeah,
okay,
Does that make sense?
yes.
PowerPoint.
So we can start now.
Okay, so we have your started on our side.
Okay.
Yes, yeah, if you can, every time you want a particular slide, give me the number. And you have the number, I can see it.
Yeah. Okay. All right. Yeah. Okay.
Can you see me,
So-
by the way?
So sorry.
Can you see me?
Yes, I can see
So
you.
I'll give you a 5 minutes time.
Okay. Perfect. So I start from slide 2, perhaps. So the one, yeah, slide number 2. Okay. So, yeah. All right. So apologies for that. So on this slide, you can see that as Peter and Sebastian were alluding to, we would like to increase the C13 polarization because the problem of NMR and MRI is the sensitivity is too low, and therefore the idea is to use a dissolution dynamic nuclear polarization. And as Sebastian said, we can dope the sample with radicals that provide electron spins, unpaired electron spins, and the polarization of this unpaired electron spins is already 100% at 1 Kelvin. And using DNP, dynamic nuclear polarization, we can cross polarize the nuclear spins, in particular C13, to reach very high spin polarization. And so this is an old physics trick, and following the dissolution, we can reach this very high polarization in the temperature of the body and use it for injection and subsequent imaging. So Peter, if you can go to slide number 3. I mean, Thomas. So slide number 3 is a presentation of the design that was necessary to start routine human experiments. And it's basically a cryogenic systems. And I will go into the details of each part, but this polarizer allows you to obtain 50% polarization in a solution that provides a good concentration for an adult of 80 kilograms. So we inject typically 40 ml of 250 millimolar pyruvate solution. And it's 50% at the time of dissolution, so when a dose starts being prepared, but it takes about 60 seconds until it's actually entering the blood flow of the patients or volunteer. So that is something to be aware of. Is the current technology makes it that you lose 2/3 of the polarization on the way to the injection. Nevertheless, you can go to the next slide, please, Thomas. The features of this machine allows to work in a clinical research environment. So it's basically a magnetic field that operates at 5 Tesla at temperature below 1 Kelvin. The advantage of this cryogenic system is there is no need to feed it with cryogenic liquid fluid, so there is no need to bring liquid helium into the system. It condenses helium with the cryocolor, so it's internal. There is a low overall heat leak, so it allows to work over a 12-hour working window, and there's an efficient sample cooling procedure. So all in all, it's fairly well automated, and it has a relatively small footprint that can be put in the MR facility. So Thomas, this is the next slide. So I won't enter the details of the cryogenic system, perhaps, but it's described here in a publication that's listed down at the bottom of my slide. The main thing is that, as I said, it's a closed system, and it has a suction pump that will basically pump on the gas to reach temperature typically 0.8 Kelvin, and can stay there for at least 12 hours, and it can be regenerated over the night, so you can recondense helium, and then you're always ready for your next experiments the following day. And yeah, please, next slide. So yeah, so one important thing, as Sebastian mentioned, is that we would like to have sterile doses, and the spin lab was designed around the idea of having a so-called fluid bath. So it's a complete closed, sealed plastic part that allows you to prepare a dose that has not been contaminated by anything. Today, we also use a filter at the end to ensure the sterility. It's a sterility insurance as well at the end. But overall, the contaminations are really limited. So that's the trick. And as Sebastian mentioned too, this plastic is complicated to manufacture because it has to resist all the different acidic environment and variation in temperature. So if you look at this, there's a part that actually goes into the low temperature environment. This vial, a black vial, where we actually introduce the substrate, the C13 substance, and the rest, the large syringe in the center of the slide, contains superheated water that we use to dissolve the frozen pyruvic acid that has been polarized. And then the receiver on the right side contain neutralization media, mostly NaOH and buffer, to neutralize the acid and buffer it to 7.5, pH 7.5, so it can be injected. The rest is about measuring the parameters, and I will do for QC, meaning the quality control, to ensure that it's safe for use in humans. And I will come back to this later. But just a detail here is that this is, if you can go to the next slide, please, Thomas. So you can see here a zoom on the vial. So we typically use 1 milliliter or 1.2 1.2 milliliters, sorry, for human injection. So 1.2 ml of pure pyruvic acid. Pyruvic acid is not only an interesting molecule for applications in metabolic imaging, as Sebastian showed, and I will give you a few examples. But also, it has interesting physical chemical properties, and one of them is that it freezes in the form of a glass. So that's something perhaps that no one mentioned yet at this point. But to have a sample that polarizes well by DNP, when you add the unpaired electron spin, so the radical, you need to make a homogeneous sample. So you need to freeze it not in crystalline matter, because if you create a crystal, the unpaired electron spin will not be included inside the crystal. They will migrate outside of the crystal. So you don't want microcrystals. So you want a perfect glass. And pyruvic acid forms a glass upon fast freezing. So when you load the liquid pyruvic acid in this vial, after you use a laser welding process to seal it for sterility. You do that in the pharmacy. And then you can quickly freeze this pyruvic acid when introduced in a cryogenic system. So next slide, perhaps. Once it's introduced inside the system, we basically monitor the C13 polarization by nuclear magnetic resonance inside at 1 Kelvin, so inside the polarizer, to ensure that the process of dynamic nuclear polarization takes place properly. And next slide, please, Thomas. Yep. I think we're still on the same slide, correct? Yeah, the one that say up to 4 simultaneous simple. Yeah, that's it. I think that's it, right? No, I see. Hold on. Yes, slide number 9. Is that right? Okay, I don't see the screen for. Okay, so the other feature of this spin lab. Thank you very much. The other feature of this spin lab is that you can polarize 4 samples simultaneously. So it should allow you to design a different type of experiments. And unfortunately, in the current design of the fluid path, we have a fairly high amount of failures. We're trying to fix those issues, but so it's hard to do really 4 samples in a row. But in some places they actually do 2 injections in the same patient, and or they can do several patients in a day. And next slide, please, Thomas. So how do we ensure that those doses are sterile? It's this quality control module. Basically, all the measurements are done optically, because this is the only way to do it fast. As Sebastian said, the polarization decays very fast, so you have to quickly be able to inject it, and so you therefore have to quickly figured out whether this is a safe dose and it has all the correct property. So we measure pH, we measure concentration, and we measure temperature and polarization, and all the concentration and pH measurements are done optically. We also make sure that the filtration of the radicals, because we don't want to inject radicals. They're useful for DNP, but we don't need them afterwards. And for safety reason, we just don't want, although they're very stable, we don't want to introduce a high concentration into patients. We need to go through a filter and then make sure that the filtration process took place in a correct fashion. So if you go to the next slide, Thomas, please. This shows you what's typically displayed on the QC module. So on top you have the pyruvate concentration. Typical sites, typical value should be between let's say 220 and 270 or 80. So that's a dose that should give you the correct property, and that is also the accepted dose across the sites following the original studies at UCSF. The pH obviously should be physiological, so typically between 7 and 8. Some sites increase a bit, and as in the pet community, sometimes the window can be from 6.5 to 8.5. That's an okay range. The EPA concentration, EPA is the paramagnetic agent, so the radical should be less than 3 or 5 micromolar. So that's the insurance of the proper filtration, and the temperature is typically around body temperature. Then also the volume that we produce is typically above 40 ml, typically 43 to 45 ml. And the polarization, as I said, it is around 50% at the time of dissolution. So that is what you get. And the next slide, please. So in the timeline, but what you do is you insert the agent inside the spin lab, dissolve it, and transfer to syringe and QC measurements. So all this take about 30 to 35 seconds. We measure the temperature, we measure pH, volume, and the liquid state NMR to measure the polarization and the concentration, as I said. And then there's a report which I showed you before. The door opens, and then you have to handle the syringe and put it on the injector, and this typically takes 30 seconds at least in all sites before they are actually triggering the injection. So next slide, please. So this is sort of a summary of the complexity of the system. So it's one thing to polarize, and it's one thing to have a high signal, but whatever solution you have to polarize your C13, you will have to go through the process of sterility, the chemistry. You have to make sure that the pyruvic acid is stable. So we work with different companies now, here Sigma or CIL, to make sure that they provide chemicals that are isotopically labeled and clean. Then we also work with plastic manufacturers to make the fluid pass. We also have to work with pharmacists who actually fill the fluid pass with the fluids and the pyruvic acid in a sterile manner. And then on the bottom, of course, in terms of hardware, there is the spin lab, which I presented, the QC also for the safety, and of course you need an MRI, and you need C13 coils so that you can measure C13 and eventually go into the humans. So next slide, please, Thomas. So currently there are 24 of these systems installed worldwide, and there are 8 ongoing clinical studies, 4 in the Americas, UCSF, Toronto, New York, MSKC, and Dallas, and 4 in Europe, in Oxford, Cambridge, London, and also 1 in Denmark, in Aarhus, where they just started their first patient study. So it's growing, and next slide, please. So the first in-human trial was done at UCSF and was published in 2013. This was not done with the spin lab. This was done with an alpha polarizers. but they looked at the prostate cancer, and it was more like a safety trial, and showed that not only it is safe to use in humans, but also that you can observe contrast with the C13 that you can observe with the standard anatomical proton imaging. And next slide, please, Thomas. In Toronto, they demonstrated that you can get stunning images in the heart of a patient, showing that the myocardium produces bicarbonate in large quantity within the time frame of the acquisition, which is 10 seconds. Yes, thank you. Next slide, please. Another application that was currently published by the group of Kevin Kishari in New York was to show that C13 lactate is produced in brain tumor in much higher quantity than any other places in the brain, and that you could use that to correlate to measure the aggressiveness of the tumor. So there are some interest on the clinical side, and yes, next slide, please. This is where we are today. It's not perfect, but it's a new technology, and we're trying to work on the simplification of the delivery and the quality control of this to reduce the delay between the production and injection. We said it's 60 seconds today. Our goal would be to go down to 40 seconds. I think this 30 seconds would be feasible, and improve hardware and methods to increase the robustness is key here, and also go beyond pyruvic acid for possible other substrates. So in general, we aim at demonstrating the clinical benefit of this technology, because that's the only way that it will become widely available, and there will be investment. And finally, next slide, please, Thomas. The conclusion is that we think that the recent results show that there is some valuable clinical information that can be highlighted using this technology. And currently, there have been around 300 people injected and scanned with this technology. It's probably going to stay in this current implementation for a year, but then we want to improve the hardware and the methods, and perhaps and I won't talk about this today, but we have ideas on how the future implementation might allow to produce the substrates at remote sites to deliver and not have a spin lab necessarily in your facility, and just deliver to the different MRI suites. And I thank you for your attention.
Right, questions? Well, let me start off with one. So you mentioned sort of future implementation at remote sites, but you want to also cut down the time. So how is this going to work? You're going to deliver it in a frozen form?
Yes, yes. Yes, that's correct. So the idea would be to perform the process of DNP at the remote site, and then keep those doses in little capsule or something that have been pre-polarized and frozen, and have a much smaller device, sort of a cryogenic suitcase, if you want. That doesn't have to be at 1 Kelvin, because you don't have to stay at 1 Kelvin. You can be in a little cold gas environment with a small magnet, permanent magnet, and be able to maintain the polarization and extract the liquid on site in a much smaller device. It would still require some process on site, but you can make it much smaller and basically really directly transferable to the patient. Yeah.
Well, the problem that I would see that then basically the quality control would take place at the final site, I guess. Well, you could do polarization measurements, well, as a fluorescence status, but all the other things, with particular, you're still diluting it and so on. So the pH and these things probably will have to be measured in the final destination, which means you would save on instrumentation there, but you still need a qualified person on site, basically.
It's not necessary. It's a good point, but it's not absolutely necessary because so one of the further developments we're thinking about would actually be based on doses that are very well calibrated. So of course you will still want probably measure the pH, but today it's done with pH paper as well. So this is a fairly simple procedure.
Measurement is simple, but it still has to be a qualified person, right? At least in the British system.
Yeah, no, you're right. I mean, I cannot anticipate exactly unless we have a device that is CE marked that will give you the pH right on the spot. So that I'm not sure how this is going to evolve. But you're right. At the end of the day, what we wouldn't want to have is a CE marked instrument saying, well, we have a way to internally within the device give you a pH that is absolutely reliable. And that would make the QP redundant at that point. But we're not yet there. So, yeah.
Well, also, of course, you could have, in pharmaceutical production, not every pill has been checked, right? You can do random checks, and even with hyperpolarized xenon, I believe, there is a quality control through video, and even that doesn't have to be done every time. But just, at the end of the day or something like that.
Exactly, and perhaps the other advantage of having pre-prepared doses, you can imagine you prepare 10 doses and you use one to do your QC in advance. So you check that all the parameters, and if you ensure that all the doses are exactly the same, because it's a batch production, then you can say, since my dose was okay, then I rely that the other 9 are similar, and therefore I go through this process. And I don't,
Sebastian, yes.
Regarding the QP, we will have one, but I believe that Cambridge and Oxford don't use the QP all the time to release any security agent. So can you comment about it? Is it because they don't do any clinical study, clinical phase 1 clinical study, or is it because they work on the physiological study? I'm confused there.
So yes, so you're absolutely right, Sebastian. So in Cambridge, what they do is when they feel the fluid path, they go with the batch mode. So they basically produce, let's say, 10 to give a number, 10 fluid paths in the same exact way on the same day, and then they freeze them all. And they take 1 out of the 10, send it for sterility check and endotoxins and so on, and then it comes back 2 weeks later. Meanwhile, the other 9 have been frozen, and if they're happy with the results from the one they send for a sterility check, then they release the other 9, and that is when the pharmacists take the responsibility of saying this is safe for use. So they change the release point is at the production time, not at after dissolution. So that's a slightly different approach indeed.
Any further questions? See, that's not the case. Well, let's thank our speaker and all of our speakers from the session again. Thank you.
Okay.
And good, you're traveling right now.
Thank you, Thomas. So enjoy your stay, and thank you for playing. Yes.
Can I call you on Skype?
Sure. Right now?
Okay.
Okay.
Why not? will listen. Or they can speak French.
So, my dear colleagues, now we are going to have a break. This is a break for an excursion to the main building of the Moscow State University. And after that, we shall have lunch.